All right, so let's talk today about integration in cylindrical coordinates. So this comes to us from section 15.7 of the textbook, but it is kind of the logical extension to dimension 3 of integration with polar coordinates. So what's the idea here? Remember, in space, we have this sort of three coordinate planes. The xy plane that comes horizontally flat out of the board, the YZ plane that you can think of as like the board itself, and the XZ plane, which comes out sort of vertically from the board. So pick one of these three coordinate planes and model that coordinate plane using polar coordinates. Then you'll have one other direction that's left over in space, and you'll just let that leftover coordinate remain as itself. So I guess the sort of most common one, or maybe the first one that we'll encounter in this course, is just let the xy plane be modeled in polar coordinates as we've done before, and let z just stay equal to z. So, um, so we'll say that r theta z are one way to put cylindrical coordinates on r cubed. Another way is to say have the yz plane be modeled in polar coordinates and then let x stay as itself, or let the xz plane be modeled in polar coordinates and let y equal y. Y will stay as itself. So it depends on, what the region is that you're modeling. But the idea is kind of that whatever region you're modeling, if it has some kind of rotational symmetry around one of the three coordinate axes, then that's the coordinate axis you want to leave as itself. And the remaining, the plane that's spanned by the other two will be the one that you choose for polar coordinates. So let's look at some cylindrical boxes. So remember that a polar box in the plane is either an annulus or a disk or a sector of an annulus or a sector of a disk. So a cylindrical box will just be a polar box in the plane just stretched out for the length of an interval. So it'll become like a solid that is just a solid whose base is a polar box and is just stretched out for some amount of height. So I think we can probably look at one of these in GeoGebra. So let's scoot over to GeoGebra. Right, here is one where the inside boundary is the cylinder x squared plus y squared equals to 1. That would be like r equals to 1. And the outside boundary is x squared plus y squared equals to 4. That would be like r equals 2. So the actual cylindrical box, the solid itself, is supposed to be everything filled in here. So these are just the two boundary pieces of it that I modeled. And, we could let z go on just for a finite amount of time. Here I haven't really specified anything because I don't know how to get it to work out right in GeoGebra that way. But, you'd think of this just being a finite height solid of this form. Looks kind of like a toilet paper roll, right? Which is super popular right now. Anyway, actually, this one looks like something you might have probably seen from Calculus 2 as well. If you think of everything is filled in there, it looks like a cylindrical shell, right? From Calculus 2. So, okay, enough of that. So you might write this cylindrical box. For example, here we were just looking at kind of this one, where r went between 1 and 2, and theta went all the way around from 0 to 2 pi, so we didn't have a sector. We had the whole thing, the whole annulus times an interval. And z, if we'd let z in the picture that I showed you, z just went on forever in both directions, but we'd like to chop z off at some finite heights. So we have just some finite volume solid. All right, good. So right, it's a cylindrical shell from Calculus 2. And if you let the lower bound for r be equal to 0, then you'd get just a solid cylinder, right? No solid annulus, just solid cylinder. All right, and so if we do the Jacobian matrix, you'll find that the first two coordinates have no z's in them, so their derivatives with respect to z are 0, and z equals z, so z doesn't have any r's or thetas in it, so its derivatives with respect to r and theta are 0. So you get this Jacobian matrix that has the Jacobian matrix for polar coordinates in the top left corner, and then zeros elsewhere except for a 1 on the sort of bottom diagonal piece. So since linear algebra is like not a prerequisite for this class, you're not really required to know how to take determinants of matrix of a 3x3 matrix. But we'll just tell you that it's really not so scary when you have all these zeros here. It's really just 1 in this top bottom corner times the determinant of this 2x2 matrix, which we already know is R. So we get 1 times R. So, oh, we get the same Jacobian determinant that we got in polar coordinates. So that's yet kind of another reason why this is a sort of logical extension of polar coordinates to dimension 3. And so let's consider, a cylindrical non-box. So a cylindrical non-box would be something of the form, a solid of the form E, which is a collection of points in space x, y, z, where maybe z varies between the graphs of two functions, g1 of xy and g2 of xy, and x and y vary over some region D of the xy plane that can be nicely modeled with polar coordinates. So, this z, it doesn't really, these functions here don't really have to behave too nicely with polar coordinates. It's just that whatever two-dimensional region D in the xy plane that your E projects to, that region should probably play nice with polar coordinates. It should probably be modeled nicely in polar coordinates. So and if it is, then you might consider using cylindrical coordinates to model your region E. So let's say that region D in the xy plane is nicely modeled by polar coordinates, and it has the form, say, the set of all r theta, where r goes between the graphs of two functions of theta, say h1 of theta and h2 of theta, and theta goes between two constant values, alpha and beta. So this is like our standard polar non-box that we saw, I think, in the previous lecture. So then for a function, f of x, y, z, that's defined over that region of space, we can take the triple integral of that function f over E by doing an iterated triple integral in cylindrical coordinates. So the thetas still go from alpha to beta. The r's still go from h1 of theta to h2 of theta. So this outer double integral is still just your standard polar coordinate kind of integral. And then your innermost integral with respect to z will go between g1 of r cosine theta, r sine of theta, right? Because that will be our x and y now. And similarly, the upper bound for that integral will be g2 of r cosine theta, r sine theta. And again, when we take f, we have to evaluate f at not x, y, z, but r cosine theta, r sine theta, and z. And again, we have to multiply by this Jacobian determinant r to account for some kind of warping of volume between the cylindrical coordinate space and ordinary rectangular space. So this is the formula. So let's see. Before we go into examples, I think I'm going to cut this video off because I want to make sure that the audio is coming out right on them. And yeah. So join us in the next bit. We'll start to do some examples.